Hello, I'm Muhammad, and today we're going to discuss this lab about trees, spanning trees, minimum spanning tree, and Prim's algorithm. So let's get started. Our agenda and objectives for today to have a quick recap of previous topics related to this one and discuss spanning trees, minimum spanning tree, Prim's algorithm, and expand on each one of these and solve practical exercises on them to strengthen our knowledge of stocks. So now let's get started. What is a tree? Does anyone know? A tree is a connected graph with no cycle. Can you state the properties of trees? A tree has three main properties, which are a tree has a unique path between any two vertices. It is minimally connected, which means that if you remove any of its edges, it's going to be two different components and not connected anymore. It's maximally acyclic, which means if you add any edge to it, it's going to cause a cycle in the graph. Okay. So what formula relates N and E in a tree, where N is the number of nodes and E is the number of edges. And we can easily notice that or observe that from trees that N equals E plus 1. Now we have a quick recap of the trees. Let's go over spanning tree. A spanning tree is a subset of graph G such that all the vertices are connected using minimum possible number of edges. So in simple words, we have a graph, we try to remove some edges from it to get a tree of the same graph, same vertices and everything, so it's all connected, but with less edges. Hence, a spanning tree doesn't have cycles, and a graph may have more than one spanning tree. So let's practice on it. Can we get all spanning trees from graph G? Here we have graph G have vertex A, B, and C are connected through edges A, B, B, C, and AC. We can have three spanning trees from this graph. We can have A to B and then B to C, or we can have A to B and then A to C, or we can have A to C and then C to B. And here are the three spanning trees of this one. Pretty easy, right? So now can you please practice on this graph and do this thing? Okay. Now let's move on to the next topic, a minimum spanning tree. So what is a minimum spanning tree? What are we minimizing about? We are minimizing for weight. What is the weight of the tree? What is the weight of a graph? The weight of a spanning tree or a graph is determined by the sum of all the edges involved in it. A minimum spanning tree is defined as the spanning tree that has the minimum weight among all the possible spanning trees. So we can see in the previous one, in the previous example, we had this one. We had a lot of spanning trees here. So if these spanning trees have weights, our minimum spanning tree is going to be the one with the minimum weight. Okay. So let's practice on it. We have this graph. Can we get minimum spanning tree of the following graph? So at first, let's get all the spanning trees, calculate total weight of each one, and then we can easily determine the minimum. Okay. For this graph, we can have A to B and then A to C. Here, with a total weight of 5 plus 6, and that's 11. Or we can have the spanning tree of A to C and then C to B, which is 7 plus 6. 7 plus 6, here it's going to give us a total of 13. Or we can have A to B and then A to C with a total of 7 plus 5, which is 4. And here we can easily see that this one is the minimum one. So this is going to be our answer. And this is going to be our minimum spanning tree of total weight of 11. Pretty easy, right? Now let's go on and you can practice on this graph. It's a simple graph with A to B1, B to A to D5, A to C3, B to D2, and then C to D4. Now, we can see that the getting all spanning trees, calculating the total weight of each one of them, and then determining the minimal one is pretty costly operation. So we have various algorithms discussing minimum spanning tree problem, and Prim is one of the most famous ones. Prim's algorithms is a greedy algorithm used to find the minimum spanning tree for a weighted and directed graph, which is pretty simple algorithm and has a pretty simple approach. What do? The algorithm operates as follows. We initialize by starting at an arbitrary single vertex, anyone. You can start at any vertex you want, and it's going to be our initial component of the MST. And then we are going to repeat steps 2 and 3 repeatedly until we reach termination. So iteration, we repeatedly add the minimum weighted edge that connects a new vertex to our MST. So we're going to go to a new place and then add this vertex to our MST and expand on its edges. Yeah, add this vertex to our MST and then expand on its edges. And then you iterate over the edges, get the minimum weight, and so on and so on, until you reach the termination state where we have all the vertices of the graph are included in our MST. Okay, so now we can practice it visually over this graph. We can use Prim's algorithm to get the minimum spanning tree of the following graph. We have this simple graph of AB2, AC3, BC1, BD4, CD5, CE6, and DE2. It's a simple graph. We can start at an arbitrary vertex. Let's start at A and see what happens. So now we add A to our MST and expand on its edges. So we have edges 2 and 3. We get the minimum one, which is 2. Does it connect us to a new vertex? Yes. So we take it and we add it to our total. And then we have this vertex being included. Let's expand on it into our MST. So we have these edges now. What is the minimum edge of the highlighted ones? Which it is this one, B2C with weight 1. Does it connect us to a new vertex? Yes, it connects us to vertex C, which is a new one. So let's take it and add C to our MST. Now we have a total of 2 plus 1. And now we have C in our MST. Now let's expand on it. We have these new edges, CD5 and CE6. So now out of these highlighted edges, what is the minimal one? It's this one. Does it connect us to a new vertex? No, it doesn't. So we are going to skip it. We don't need it. So we're going to go to this edge 4. That connects B and D. Does it connect me to a new vertex? Yes, we take it and we add D to our MST and expand its edges. This one too, and now we have total of 2 plus 1 plus 4. Now, what is the minimal edge? It is this one, 2, that connects us to vertex E. Does it connect us to a new vertex? Yes, we take it, and now we have a total of 2 plus 1 plus 4 plus 2, which is 9. Now we have reached the state of termination where we have all the vertices A, B, C, D, and E of the original graph. We have them in our MST, so we can easily terminate. And now this is our minimum spanning tree with a total weight of 9. And now, as an exercise for you, please try starting at another arbitrary vertex and observe the journey and the result at the end, and see if we have the same result. Does it affect it? What happens to the journey and the same and everything. So please try it. And now for extra credit, we have I have this snippet of pseudocode of Prim's algorithm. It's basically the same thing. We start with having MST at vertex S, which is our starting point. We have no edges yet, so our T is empty. We continue until we have all the vertices that are in the original graph. We select an edge, UB, that belongs to the set of edges where weight is the minimum, and U belong to where U belong to R and V doesn't belong to R, which means it connects our current R to a new vertex that is not in R. And then we add this edge to our set of edges, and we add this vertex to our set of vertices. Now we can use this pseudocode as a guide to implement Prim's algorithm and submit it to this problem. It's a very simple, straightforward MST problem. If you do it, you will get extra credit. To read more about other algorithms that are related to minimum spanning tree, maybe have a comparison between them, comparison according to time complexity, memory, anything, you can read about Kruskal algorithm and try to solve the same problem Spoj with the Kruskal algorithm and send us both submissions. And now, as a recap, a summary of what we did today, we've done a quick recap of previous topics, and we discussed topics of spanning tree, minimum spanning tree, Prim's algorithm, and solved some various practical exercises. I hope that they were helpful. And now we are at the end of our lab. If you have any questions, please address them to me now. And if not, we can go on with you. Please, you can start on your exercises, and you can maybe have some more fun with some challenging exercises. Good luck and goodbye.